Hello, everybody, and welcome to Mr. Saucedo's YouTube videos. We're going to be talking about population growth and specifically how do populations grow and shrink. So, population density is the amount of individuals that are living in a particular area. And so, you may have seen a population density map. The darker the area, the more people live in that county. And so, you can see that there are a ton of people on the West Coast and East Coast, a lot of people in the Midwest here, or I guess is this the Midwest? I guess this is like the South. This might be considered the Northeast. I guess this is probably more the Midwest, but the Midwest has way less people, right? That's kind of in general how population density works in the United States. And so population density is calculated by the number of organisms per unit of area. And so remember that area is a unit squared. It can be any unit squared. Here you can see it's population per square mile. So this is number of people per square mile. Here's a color-coded little chart so you can kind of see the distribution. Again, notice there are a lot of people along the coast and then less people inland. That might be Orlando. That might be like Disney World area right here. Maybe that's why there's so many people. So again, just population density is equal to the number of organisms divided by the unit of area. And so here we go. Here's our plot of land. We have a 10 meter by 5 meter plot of land. What's the population density of this, plot of land? Well, let's count how many organisms we have. And let's divide by the area in meters squared because these are both meters. So count, and I got 21 organisms. 10 times 5 is 50, so 50 square meters. That's about 0.42 organisms per square meter. And again, this is a totally appropriate way of writing population density. Population dispersion, how spread out are individuals? Well, there are a couple of main ways of tracking population dispersion. So we have clumped, uniform, and random. Clumped is exactly what it sounds like. It's they're all in a little group stuck together, or they're in little groups stuck together. Uniform, they're evenly spread out. Random, there seems to be no pattern. So here you can see this is a clumped distribution. So we've got your little clumps of stuff here. Uniform is where everything is spread out evenly. And then random, there doesn't seem to be a pattern. And so where might you find uniform distribution? Well, you might find that when you have a bunch of birds laying eggs, they will make sure that they are just out of pecking distance of any other bird. When would you see clumps? Well, maybe in a school of fish, in a swarm, something like that. Obviously, I can't show anything that has random distribution, but sloths have random distribution. So that might be a good example. Now, what are the 4 factors that affect the size of a population over time? Well, the 2 most obvious ones are births and deaths, right? So the more births you have, you're increasing the number of individuals. The more deaths you have, the more you're decreasing the number of individuals. But there are 2 other ones, immigration and emigration. Immigration is movements of individuals into a population, so their population goes up. Emigration is the movement of individuals out of a population, so the population goes down. Keep in mind, immigration and emigration, though, wherever they are moving to, that goes up, but wherever they're moving from goes down. And that's the opposite for emigration. Wherever you're moving to, that population goes up. And again, whatever you're leaving, that's going down. And so it's something that you can track, though, the population over time. Here's an example of a population graph of wolf and moose on an island in Canada. And so you can see the number of moose and wolves going up and down as time goes by. Now, there are 2 general shapes of population growth. We have exponential growth, where we have population growth that occurs extremely rapidly for a short period of time, something like this. The number of rabbits reproducing, so this is an exponential growth curve. Humans, this is human population. So you can see that it's kind of going up like this. You can see here, though, that if we're looking at average population increase, it looks like it's going down a little bit here, but again, you get the idea of just how exponential growth looks. Organisms that reproduce quickly tend to have exponential growth. Obviously, we are not in that category, but there are plenty of good examples like bacteria, viruses, rabbits, mice. That tends to be the direction that population growth goes for them, is exponential. Logistic or stabilizing growth, though, That is where we have slow growth, exponential growth, and then it levels off to a stable size. The stable size that we're looking at, we normally call that the carrying capacity. And that is the maximum level of organisms that a habitat can support. And so, depending on your calculation for this, it can be a lot of things. So, here we have paramecium population in a laboratory culture. So, obviously, there's not enough space for them to keep, reproducing forever. And so, it starts to level off over time. Here's again Daphnia. You can see it in a laboratory. It starts to go and level off. Fur seals, and so you can see the fur seal population is going up like this, and then it starts to stabilize also. And so things like fungi, sheep, seals, all tend to have logistic or stabilizing growth. Well, what happens when we exceed our our population's carrying capacity? Well, when you exceed it, we get what we call a population crash. And that's normally due to a lack of resources. So you can see this is the population. Let's say this is the carrying capacity. So you're exceeding the carrying capacity. There aren't enough resources for your population. And so it doesn't go down immediately, but eventually it reaches a peak. And then there is what we call a population crash. And then generally, as resources become more available, eventually it'll start to go back up, and eventually it'll stabilize though. So it'll go back up and then it might crash again. It might go back up and crash again, but it eventually will stabilize to this dashed asymptote line.